In this video, we're going to go over some applications and some problems that are kind of typical problems that have appeared actually in previous exams in previous years on sections 2.4 and 2.5, which is what we just covered. So I just wanted to complement everything with applications, some more examples of more problems. One for such problem, and this is kind of a typical thing, is you will be given function defined in a piecewise way, and it will depend on a parameter, and you'll be asked to find the value of that parameter so that the function is continuous. So in this, for this particular problem, you're given a function f of x, which is equal to ax plus 2 for x less than or equal to 3, and equal to x squared plus 2a for x greater than 3. And you're asked to find the value of a for which f is continuous. At x equals 3. There are some other variants of the problem where they ask you to find the values of a such that f is everywhere continuous, and since usually the functions involved will be of this form, will be polynomials, which you know they are continuous everywhere. So it will reduce to the same thing, just checking what happens at the transition points. So it's kind of all the same. So you know that the function is defined a certain way for values smaller than or equal to 3 and greater than 3. And those two expressions are continuous, so you have definitely left and right hand limits, and you have to make sure that the value of the function and those left and right hand limits are equal to each other. Okay, so let's try to solve this problem. So let's try to see. The first thing is to check that f of 3 is defined. Remember that we need a few conditions in order to say that f is continuous at the point 3. Yes, f of 3, if you go back to the rule, when x is less than or equal to 3 and 3 is less than or equal to 3, it's equal to 3. So this formula here includes the value of x equals 3. So when x equal to 3, f is equal to a times x plus 2. So what do we do here? We multiply a times 3 plus 2, which is just 3a plus 2. So it is defined there. So that's the first thing that we need to check. Secondly, we need to check that the limit of f of x exists as x approaches 3. Well, we computed two one-sided limits, so the limit from the right. When x is greater than 3, we have to use this formula. This is what so this is what this formula says. I mean that when you're greater than 3, f of x takes on this form that I'm putting in a bubble. So we need to use that when we compute the limit, the limit from the right. So, and that's equal to x squared plus 2a. But this function is continuous, so we can use substitution. And we just plug in 3 squared plus 2a, which is 9 plus 2a. Okay, so this is the right-hand limit. Now we also need to compute the left-hand limit. The limit of f of x as x approaches 3, but from the left. But here, if x is less than 3, then it takes on this form. And we're approaching x from the left, meaning from the side where values of x are smaller than 3. So we need to use that formula for f. X plus 2. This 2 is a continuous expression, so we may use substitution again, and we get a times 3 plus 2. So we also need, in the third step, let's notice here that this is already the value of f at 3, which we checked in the first step. Okay, so we just need to check that these two expressions, so this expression over here and this one in bottom, agree, because then the function will be continuous. The point. Remember that one of the one-sided limits already agrees with the value of the function, so we just need to make sure that the limit exists, meaning that the one-sided limits are equal to each other. So we need that the left-hand limit is equal to the right-hand limit. So we may subtract 2a on both sides and subtract 2 on both sides, so we get that a is equal to 7 and so then if a is equal to 7, the limit of f of x as x approaches 3 is equal to f of 3. And this means f is continuous at x equals 3, which is what we wanted. Also, this is a very common and typical type of problem that you will see during exams, quizzes, and all sorts of evaluations. But it basically reduces to looking at the transition points and making sure that the right and left hand limits are equal to each other and that the value of the function agrees with this limit. So that's it. Another kind of, the kind of problems you'll be asked to solve involves the computation of limits. So, the problems coming from section 2.5. So, computing limits. So we see several examples that come from the book. Okay, some of you have already seen. This is happens. So happens that most of the algebraic expressions that we can manipulate have to do with rational expressions. We are dealing with radicals or polynomials that can be factored out. So we're gonna see some less common examples as well. So one such a example is the following. So suppose you're asked to find the limit as x approaches 5 of 2x squared minus 9x minus 5 over x squared minus 25. That is equal to. So what the first thing we need to do is to see what happens when we try to plug in 5 into this expression. X squared, so we look at the denominator, 5 squared is equal to 25, so the denominator vanishes, But what happens when we plug it into the numerator? We get 2 times 5 squared, which is 25. So we get 25 times 2, so see, 2 times 25 minus 9 times 5 minus 5, and this is equal to 50, and this whole thing is equal to minus 50, so you also get 0. So this is an indeterminate form, so we cannot just proceed by substitution, and we need to do something else. We need to some algebraic manipulations. It leads to an indeterminate form, 0 over 0. So what do? We try to eliminate the offending factors in the numerator and the denominator, and so we need to factor this out. 2x. So we know that x minus 5 is going to be a factor, and 2x is going to be another factor, so x minus 5 on top, x minus 5, x plus 5 on the bottom. Okay, so what do you think is the number here? It's 1, so 1 times x, so two numbers of minus 5 times 2x gives you minus 10x, plus 1x gives you minus 9x, which is what we have here. And if we multiply 1 and minus 5, we get minus 5. So we've found a factorization of this expression. It allows us to compute this limit. So now that we've become experts at doing this, we simply go ahead and simplify this. Remember that we never allow x to be equal to 5. So we just compute the limit now of when x approaches 5 of 2x plus 1, x plus over x plus 5. Now we need to check again. What happens if we have a quotient? So if we want to use the substitution method, we have to make sure that both quantities are continuous. So x plus 1 is continuous, right, everywhere, and x plus 5 as well. But when x approaches 5, the bottom is no longer equal to 0. So we can apply the law for the quotient, and we simply obtain that this is equal, and we can just substitute 5 into x. We get 11 over 10, which is our final answer. Okay, so another less common type of problem is the following. So limit when t approaches 0 of 4 to the 2t minus 1 over 4 to the t minus 1. Again, this is an indeterminate form, 0 over 0, because when you plug in 0, 4 to the 0 is 1. So 1 minus 1 is 0 on the top, and 1 minus 1 is 0 on the bottom. But to compute this limit, we can still do the same thing. We just note that 4 to the 2t is the same as 4 to the t squared minus 1 over 4 to the t minus 1. But now we can write 4 to the t squared minus 1. Well, 1 is the same as 1 squared, so this is the same as 4 to the t minus 1 times 4 to the t plus 1. All of that, this is divided by 4 to the t minus 1. So we may cancel this again, keeping in mind that t is not equal to 0, so 4 to the t minus 1 is not equal to 0. So we may cancel this. And now we can use substitution, because 4 to the t is continuous. It's in our list of functions that are continuous. in their domain, and the domain is the whole real line. So we may use substitution here, and we're gonna get 4 to the 0, is plugging 0, plus 1, evaluated 0, which is just 1. And this is just equal to 2. 4 to the 0 is 1, so 1 plus 1 is 2. So that gives us that limit.